Chalo, let us begin, everyone. Now we will be starting with the fourth unit of the topic. And for our convenience, I have divided this unit in two parts. Part one, which we'll be doing today, and part two, we will be completing in tomorrow's lecture. So here we will be having a topic based on imperfections, or what is known as defects in the solids. Now, whatever solid structures we have seen so far, that is, let us say, face centered cubic, body centered, whatever 3D structures we saw, everything we call as a perfect crystal. Perfect crystal is what we expect in theory, and it exactly seen in reality. As we know that there is nothing called perfect in fact. So we expect a perfect crystal with a precise geometrical manner pattern, lattice point perfectly occupied, having a perfect geometry, perfect stoichiometry. Basically, in reality, that is just a dream. What we have in reality is called crystal with defects. That means exact lattice point won't be covered over there. There will be imperfections. So any deviation from the orderly pattern or stoichiometry of the arrangement of atoms is called defect or the imperfections. Any doubt so far? Go through this paragraph. Everything all right? So what sort of defects we can get? So under defects, this is a quick summary of all the defects roughly written. They are mainly of three types. One, the impurity defect. Second, stoichiometry defect. And third, non-stoichiometry defect. Now, stoichiometry defect and non-stoichiometry are further subdivided. Even impurity defects also are subdivided, but in this chart it is not given. So we will now take up around totally 7 to 8 type of defects under this. We will start learning first of all stoichiometric defect. Now by stoichiometric defect we mean that defect might be there, but the formula of the solid crystal, stoichiometry of the solid will not be disturbed. That's why they are also known as intrinsic defects or thermodynamic defects. They are of following four types. Number one, vacancy defect, interstitial defect, Schottky defect, Frenkel defect. Actually speaking, vacancy and Schottky defect are identical. Interstitial and Frenkel are identical. So why do we classify them? Vacancy and interstitial are found in non-ionic solids. Non-ionic. So for example, magnesium, aluminium, sodium, these are the crystal without any charge on them. They will show vacancy and interstitial, while Schottky and Frenkel are seen with ionic solids like sodium chloride, potassium nitrate, where you have a cation and an anion separate. That is called, that will show Schottky and Frenkel. So let us start now one by one with these four defects. First one, vacancy defect. As the name suggests, instead of a perfect crystal lattice, we will have vacancies in between. For example, if this is imagined to be a perfect crystal, instead, what you see in reality is something like this. There will be vacancies, atoms missing from certain points. Now, due to vacancy defect, density of the substance will decrease. And this defect can be artificially created by heating the substance. I think one of the easiest defect to understand, vacancy defect. The next is called interstitial defects. In this one, there will be some constituent particle which will change their position and the atoms are present in the interstitial site. For example, if this is the perfect crystal, then instead of this, you will have atoms placed in the interstitial spaces. So atoms from elsewhere will be dislocated and sent over here. So perhaps what we saw in the previous defect as vacancy Those vacant atoms have elsewhere gone as an interstitial defect also. So these two defects are linked with each other. They will increase the density, and if this defect is possible, because void space has to be little larger, and in that large void space, atoms can be perfectly fitted. Now remember these two defects very well. Vacancy defect, where you see the vacancies. Interstitial, where interstitial spaces, void spaces, are filled with atoms. Remember them. And now check the next one, Schottky defect, and you will see a tremendous similarity. Ionic crystal is imagined to be A plus and B minus, cation and anion. And equal number of cations and anions go missing. So this is ideal crystal structure. From this, one cation and one anion goes missing. Now this condition you can see is Schottky defect, which indirectly, if you check, is just like vacancy defect only. Moreover, when Schottky defect is possible, when you have high degree of ionic compound, coordination number is as high as 6, 8, or 12. Difference in the size of cation anion is small. And examples of these are KCl, NaCl, AgBr, and so on. Keep these examples in mind. And when we go to Frenkel defect, you need to remember them once again. What are the effects of Schottky defect? Due to this, number of ions will decrease, volume remains same, so density will decrease. Due to the vacancies created, vacancies are known in electronic science as holes. In electricity, it's called holes. So due to these holes, electricity conduction becomes possible. But on the other hand, due to the vacancies created, stability of the crystal comes down. After Schottky defect, we go to Frenkel defect. Frenkel defect is just like interstitial defect. Ion will go missing from a lattice site and elsewhere it will be found. So for example, if this is the original crystal structure, now you will see the difference over here. Ion is missing, ion is still elsewhere. For simplicity, I have just moved an ion from one side to the nearest one. In reality, it can go at a little longer distance also. Just like other informations, since size of cation is very small, that can move a little bit quickly. So usually cations get migrated and they will be seen over there at the interstitial site. Watch the examples. Can anyone tell me what do you see a similarity in over there?
AgCl and AgBr.
AgCl, AgBr. I will go back for a moment just to show you the examples over there. Check which example is common.
Only Ag.
Yes, AgBr. The question asked in NEET, JEE, CET, HSC everywhere. Which substance can show both the defects? There is only one answer, that is AgBr. Please remember it. The effects of Frenkel defect. This defect is present in those compounds which have low coordination number. That means coordination number of around 3, 4, or sometimes 6. Also, large difference in the cation and anion size must be there. Solids can conduct electricity to a smaller extent, not very much. And density doesn't change because of Frenkel defect. Once again, since holes are produced, the stability of the crystal goes down. We come back to this chart again. We have completed all the 4 stoichiometric defects: Schottky, Frenkel, vacancy, and interstitial. We now move on to the next one, the non-stoichiometry defects. For exam point of view, this answer set is rather more important because it's a little bit complicated. So let us begin with this one now. In non-stoichiometric defect, whatever imperfection will be there, it will basically change the formula of the crystal. The crystal formula, properties, sometimes color, sometimes electrical conductivity will get definitely changed. They are of following types. Number one, metal excess defect, under which you have two types: anion vacancy, extra cations, metal deficiency defect. This also has some further points, but we see in the slides. So we'll see around four type of defects under this. So first we have anion vacancies, also known as F center. Now a negative ion goes missing from a lattice site, but there is no hole created as such. Instead of hole, there will be an electron present. So charge wise, it will remain same, but ion will be missing. So this is called anion vacancy. Now, when free electron comes in the crystal, the colors of the system changes. And color in German language is called Farbe, F-A-R-B-E. That's why the name is F center. This is the center which is causing the color. So for example, if this is the original crystal structure, watch over here, one of the ion goes missing, an ion goes missing, in place of which electron comes here, due to which color of the system changes. Please go through this. We'll go on more in the next slide. Let us see some examples of this. When NaCl is heated with sodium vapor, you can see sodium will get deposited on the surface. Chloride will diffuse to the surface, combine with sodium, and it will lose an electron. To understand this, let me show it over here like this. What the description tells you. Here you have, suppose, sodium chloride crystal structure, and this is sodium cation, chloride, sodium chloride, and so on. So this is the ideal structure what is present. Now imagine we send sodium vapors on the surface. So getting attracted, one of the chloride ion moves to the surface. So what sodium will do over there? Sodium will undergo oxidation. This Na will combine with this Cl, and this electron comes in place over here. So if you ignore all these additional things, what clearly we can see is chloride comes out of the system, electron get in place of that. So now the system look like sodium cation, electron, cation, electron, anion, and rest of the system becomes as it is. Now due to this one, the whole crystal, the color from white becomes yellow. This is what you know, and this center is what you call as F center. Those who want to take a screenshot of this additional description, you can take it. Please read this information now once again, see if it matches exactly with the diagram.
So we'll go back 1 second.
Yeah. Done. One or two more examples for your remembering. Excess of lithium in LiCl produces pink color. Potassium with KCl produces violet color. So this was about the first defect called F center. Next, we have extra cations present in the interstitial site. So extra cations along with their electrons can occupy the void spaces, just like Frenkel defect. So this was the original picture as usual. And now instead of this, you have additional cation with electron. So this changes the property of the crystal. Let us see an example of it. Zinc oxide solid when heated. Here you have zinc cation, oxide anion. So when you heat it, this reaction takes place. Here, this is that zinc cation, and this is the electron which are getting trapped, due to which electrical conductivity will increase. I hope यहाँ तक ठीक है सबको. Next is extra cations once again, but over here we have a little difference. The cations which you have will have different charges. This can happen when a particular element can exist in variable valency. For example, Fe can exist as +2 as well as +3. Copper can exist as +1 and +2. So in this case, suppose you have this particular original site. And in this one, now you make a change over here. I repeat this again. This was originally +1 cation, now replaced with +2 cation. In this case, now you have a mixture of +1 valency ions and +2 valency ions, due to which the formula totally changes. Now the new formula, what you get, somewhat like this. FeO will exist in a range of 0.93 to 0.96. One of the common example available is 0.95. This is because ferrous and ferric both will be present in certain ratios. I will be solving a numerical problem at the end to find out what is the actual meaning of this 0.95. So these are called what you call as non-stoichiometric formulae. Another compounds usually which show, they are all mostly transition elements which can show this. Ferrous sulfide, nickel oxide is another example which can show such fractional things. Another one which is not mentioned here, it is in 11th standard hydrogen chapter, that you can get hydrides with this non-stoichiometry formulae also. We now come to the last part after this, that is impurity defects. So under impurity defects, you can have now two categories. You can introduce an impurity, that is foreign atoms, at the lattice point or at the vacancies. So accordingly, two types are possible. Introducing impurity in covalent solid, they will produce p-type and n-type semiconductors. Have you done in physics this part, p-type, n-type semiconductors?
Yes, sir.
Have you heard of this? Yes, electronics, we use this very commonly. And second is impurity introducing in ionic solids. Now what we have done is, current topic, today's lecture, we are only discussing number 2. In next lecture of solid state, which is the last part, electrical conductivity, we will be studying number 1, because that is connected with semiconductor things. So let us begin with this part now, impurity defect. So in this ionic solids, impurities are added. They will be usually in place of host ions. By impurity, don't imagine something wrong. By impurity, we mean other element, other ion. For example, if this is a crystal of sodium chloride, what we are going to do here is remove a sodium ion and place it with strontium ion. Now, what difference does it make? Watch. Sodium is having a charge of +1. When you replace it with Sr, it has a charge of +2. So to balance the charge, one sodium ions goes away. That create a vacancy. This is called the impurity defect. This is an example, just same thing explained over here. Let us come to another defect that is called substitutional defect. In substitutional defect, we are going to have the placement of different atoms in place of the host atom. So for example, this is originally a crystal of copper, and from copper you remove the copper atoms, place some other element like zinc. This is an example of brass. So in brass, in every row, watch carefully, every row there is one zinc and three copper atoms. Check any column, any row. When you direct it, when you draw it in exam, in case HSC this is asked, आपका डायग्राम एकदम परफेक्ट होना चाहिए. एवरी रो में ये जो आपको कलर दिख रहा है ये है जिंक, और जो ब्लू कलर दिख रहा है दैट इज कॉपर. सो 3 कॉपर 1 जिंक, 3 copper 1 zinc, check any row. So if you draw in some other manner and if doesn't come exactly 3:1, then the diagram goes wrong. This is called the substitutional impurity defect. The last one under this is called interstitial. In interstitial, you have originally a crystal lattice, and in the interstitial points, impurity atoms are added. For example, in this one, we introduce carbon atoms. So this is originally iron crystal lattice. Introducing carbon gives you stainless steel. So this is one of the example of interstitial defects. We have completed all the defects. In numericals, we have only two types. HSC students do not have these problems. Only NEET and JEE people have. Very simple one. आप समझ लो सब लोग, so that you know your theory becomes little strong in this. NaCl is mixed with 10 raised to minus 2 mole percent SrCl2. What concentration of cation vacancies are created? What am I talking over here? Let me show you in the diagram, this one. When we said that strontium was introduced, there was a vacancy created. Now they're asking a problem on this, that if you are introducing 10 raised to minus 2 mole percent SrCl2, how many vacancies are created? अभी जो प्रॉब्लम मैं आपको सॉल्यूशन दिखाने वाला हूं, प्लीज रिमेंबर इट लाइक अ स्टैंडर्ड मेथड. व्हाट विल चेंज इन एग्जाम इज ओनली दिस नंबर. बाकी कुछ प्रॉब्लम में चेंज नहीं होगा. 10 raised to minus 2 mole percent means in 100 mole of NaCl, 10 raised to minus 2 mole of SrCl2 is present. We convert it into mole, 10 raised to minus 2 upon 100. And now you multiply this by Avogadro's number, you will get corresponding number of moles. That is all we do in find out. So these many vacancies are present in that 1 mole of the crystal. We go for second type. What we saw as that 0.93, 0.95, this is a very popular sum. 2019 में नीट में आया था, 2020 में जेई में आया था. They ask this very frequently, लेकिन खाली नंबर चेंज करते हैं, कभी 0.93, कभी 0.95. So overall process remains same. Understand the trick. नहीं समझा तो पूछा, I will repeat it. 0.93 का मतलब है 93 Fe atoms with 100 oxygen atoms. Steps by heart करना इसका जो बोल रहा हूं. So FeO when you write, it means actually ferrous and oxygen. So हम लोग को जो पूछा है वो फेरिक का कॉन्सेंट्रेशन पूछा है. So ferric we will consider X, ferrous we will take 93 minus X. अगर किसी और प्रॉब्लम में ये 0.95 है तो ये हो जाएगा 95 minus X. Now we have total charge of all the cations. It should match with the total charge of all the anions. अभी काउंट करो, Fe plus 3 का टोटल चार्ज कितना है? 3 into X. 3 charge, X ions, so 3X. 2 charge, 93 minus X. ऑक्सीजन का चार्ज 2 और 100 ऑक्सीजन. Solve this algebraic equation to get answer of ferric ions. सो फेरिक के 14 आयंस, फेरस के 93 माइनस 14 आयंस। यहां तक किसी को कुछ भी ट्रबल है, यू कैन आस्क मी बिफोर आई गो टू दिस सेकंड पार्ट ऑफ द प्रॉब्लम।
सर इन द सम दे आस्क ऑफ Fe only ना।
कुछ भी हो सकता है ना, चलेगा ना, क्या होता है, कुछ भी डालने दो। तो जो एलिमेंट है उसके दो, सपोज कॉपर लिया मैंने, तो कॉपर का +1 +2 रहेगा, तो एक कॉपर +2, दूसरा कॉपर +1, वैसे ही करना है, सेम टू सेम
तो
प्रोसीड
चार्ज विल
करना है।
डिफर अकॉर्डिंगली ना।
हाँ, यस। तो आपको वो चार्ज, ये सब्सटेंस पर से समझ में आएगा, ये जो सब्सटेंस है ना, इस पर से आपको चार्ज समझ में आएगा, समझा? जैसे फॉर एग्जाम्पल, आई शो यू अनदर एग्जाम्पल इन केस यू गेट कंफ्यूज, लुक एट दिस वन। लेट अस से कॉपर का +1 है और कॉपर 2 का +2 है, तो इसका ऑक्साइड का फॉर्मूला होगा Cu2O, इसके ऑक्साइड का फॉर्मूला होगा CuO। तो अगर उन्होंने मुझे इस तरह से दिया, तो व्हाट आई अंडरस्टैंड, दिस इज -2, दिस इज +2, सो +1 विल बी इम्प्यूरिटी। तो मैं +1 का नंबर जो है वो x करूंगा, और +2 का नंबर हो जाएगा 93 माइनस x। If you have followed this, you can take a screenshot, a little different type. इस तरह से आपको कोई भी प्रॉब्लम है, इस तरह से टैकल करना है।
तो सर if Cu+1 is used in that, so
तो
Cu+2 will be X ना।
हाँ, करेक्ट, जिस जो दिया है वो दूसरा ऑक्सीडेशन स्टेट, उसका इम्प्यूरिटी। सो दिस वाज द फर्स्ट पार्ट ऑफ द प्रॉब्लम, जिसमें हम लोग ने सिर्फ नंबर्स निकाला। अभी हम लोग को परसेंटेज निकालना है, तो सेकंड पार्ट वी गो। सो अभी अपना ये जो नंबर निकले थे वो था कितना, फेरस का 79, फेरिक का 14, याद रखो। तो अभी फॉर्मूला क्या बन गया, देखो, फॉर्मूला हैज बिकम फेरस 0.79, फेरिक 0.14 O। सो नाउ वी आर मोर क्लियर कि ये जो 0.93 है, दिस इज मेड अप ऑफ टू सब्सटेंसेस, 0.79 ऑफ फेरस, 0.14 ऑफ फेरिक। अभी हम लोग इसका मॉलिक्यूलर मास निकालते हैं। फेरस हो या फेरिक हो, Fe का एटॉमिक मास इज 56, टोटल 0.93, ऑक्सीजन का 16, तो ये हो गया टोटल मोलार मास। इसमें से फेरिक का कंट्रीब्यूशन कितना है, 0.14 इंटू 56, बस इसका भी परसेंटेज निकालो, ये आपका फेरिक का परसेंटेज। दिस इज द मोस्ट स्टैंडर्ड प्रॉब्लम यू कैन गेट इन दिस टाइप। अभी भी आज तक जितने प्रॉब्लम्स आए, दे आर ऑफ एग्जैक्टली सेम टाइप, नो डिफरेंट थिंग यू गेट।
सर रिपीट दिस पार्ट once।
यस, सी वंस यू कम अप टू दिस वन, आपको ये पहले वाला नंबर आ गया ना, यहां तक आ गया 79 एंड 14। तो ध्यान में रखो, फेरस का 79 है, फेरिक का 14, तो इसको पकड़ के हम लोग फॉर्मूला लिखेंगे 0.79, 0.14 एंड ऑक्सीजन 1। सो फर्स्ट स्टेप आफ्टर दिस, यू फाइंड मॉलिक्यूलर मास। सो 0.93, एटॉमिक मास 56, ऑक्सीजन 1 एटम 0.16, तो ये हो गया पूरा एटॉमिक मॉलिक्यूलर मास। अभी अपने को क्वेश्चन पूछा है परसेंट ऑफ फेरिक, तो इसलिए मैं फेरिक का मास निकालूंगा, 0.14 इंटू 56। सपोज मुझे उन्होंने फेरस का क्वेश्चन पूछा, तो मैं ये 0.79 इंटू 56 करूंगा। बस अभी खाली आप परसेंट निकालो, 7.84 अपॉन 68.08 इंटू 100, तो इतने परसेंट फेरिक। चलो अगर आपको फेरस भी पूछा, तो 100 में से इसको सबट्रैक्ट करो, दैट विल बी रिमेनिंग फेरस परसेंटेज। Is the problem understood, everyone?